Okay, so today I will show some results that we obtained using the Sloan Digital Sky Survey, but the new reduction, the photometric reduction. This work is mainly in collaboration with my student, Alan Mertz, that he has done the big work on this. So it has been known for a while that the Sloan photometry is affected by sky subtraction problems. Not only, but it depends also, especially for the bright galaxy, it depends also on the model that you use to fit the surface brightness of the galaxy. So this shows just the variation luminosity that you have. For example, just using the Sersic profile and the Sersic exponential profile, is the green line here, you see that at the very bright end, you can have a difference of 0.2, 0.3 magnitude. If you use, for example, the difference between the Sersic and the Gaussian, you get much larger differences, up almost to a magnitude. So you have to be very careful to the photometry that you use, not only about the sky problem that Sloan has, but also on the fitting that you do. This is just the dependence on the sky, not only Sloan, but also, for example, the CMAR, the tall sample, they are affected by the sky subtraction. And the main reason is because they fix the aperture where they computed the sky to some like 2000 pixel or 20,000 pixel to some fixed size. While what we do is to rescale our cut of the image based on the Petrosian radius of the galaxy. So if a galaxy is bright and nearby, we will cut a much larger frame. So you can see that at the bright end, both in apparent magnitude and absolute magnitude, we can have up to 1% of sky difference, which is a lot. And you know, this problem doesn't affect only the total magnitude, but it affects also, for example, the Sersic index that I will show you later, I will use through my analysis. This is from the CMAR sample. You can see, due to the sky, they get this strange radix-shift evolution in the Sersic index, which is not real. When we use our sample, that for which we account properly on the sky, this evolution disappears. Okay, so just, you know, we just submitted, so now the data are public. We have this catalog for which we compute not only the Vacular, but the Vacular exponential, Sersic exponential profile of all the galaxies in Sloan, the DR7. And the nice thing of this is that we have also a tool which allows to, for each galaxy or a list of galaxies that you use, to produce this kind of plot for which you see the real object, the zoom in, the model, the residual, and the one-dimensional profile that we do. So you can, if you have a list of objects for which you are interested, you can look if the photometry was properly computed, which was not possible before with Sloan. So I was happy to see that an independent work made by Kravtsov et al. They use like a few bright cluster galaxies, and they computed their own photometry. And then they compare to our and to CMAR, so their profile is the solid line here. Our profile is the long dash, and CMAR is the short dash line. You can see that for this galaxy, we are in good agreement with this measurement. Okay? And so you can see the same thing from that plot. So I was happy to see this. And obviously, due to this change in the photometry, you get a change in the luminosity function, in the stellar mass function. So this is just to give an example, so which depend on the sky, but also especially, I would say, on the fit that you use, especially for the bright galaxies. You can see that the tail here, the luminosity function, change a lot, going from a Sersic, this is us, and the blue line is the CMAR sample. So the difference between us and CMAR is mainly due to the sky, but there is a huge difference compared to Petrosian or C-model magnitude computed by Sloan. So obviously, if you have a difference in the luminosity, you will have a difference also in the stellar mass function. And this difference is not small. And so we know that in the stellar mass function there are other uncertainties, uncertainty due to the IMF, uncertainty due to the stellar population, due to the templates that you use, but there is still a large uncertainty in the photometry, so people, they have to be careful about that. And so here you can see, for example, this obviously is at a very bright end, very large masses. You can see the number density, how it changed, going from, for example, the Trojan to a Cercic profile. You can see that you have a very large factor when you are at very large masses. And this is what Krause et al. Computed using abundance matching. This is the ratio between the central stellar mass and the mass of the halo. And the red are using their values, and the abundance match was computed using our stellar mass function. And you see the agreement is quite good. So I just want to say that this not only has an impact on the HOD, stellar mass and halo relation, but also probably required less feedback because we have more stars there. So the stellar mass is actually larger than what people thought before. Okay. So with our photometry, the other thing that we tried to do was to try to understand a little bit also the assembling of massive galaxies and the growth of sizes. It has been known for a while now that galaxies at a high redshift like between 1.5 and 2, they are smaller. Not all of them, but part of them, they are a factor of 3 or up to 5 smaller. This has been a very hot topic in the literature. I would say that probably in the last 5 years or so there has been a paper a week on this subject, so you can imagine what is going on. Many people now like to think that this growing size is explained by the inside-out growth scenario, where we have the bulk, the main galaxy that has been formed at high redshift, and now it keeps assembling and growing in size by minor mergers, and in that way increase the size of the galaxy without changing too much the mass. Related to this, a few years ago, I had this work where I always use Sloan. I showed that there are two important mass scales. One is the 3 × 10⁻⁻ solar masses that was already been seen or detected by like Kaufman 2003 or so. But the other important mass scale that we saw in this work is that there is this 2 × 10⁻11 scale where galaxies start changing properties, like in the size, they start being larger, velocity dispersion become a little bit smaller, super brightness, change in color, change in the ratio between the minor and major axes, and also in the color gradients. So our idea was that at the low end, below 3 × 10⁻10 solar masses, probably will start being dominated by still wet merging. There is still some gas, galaxy become a little bit bluer, and there is, you see the size become larger. So we are dominated probably by a little bit of this component there. The big question is what happened at the large masses. So these are probably galaxy objects that grow through dry mergers. The question now is, are these mergers major or minor? More recently we saw also that these two mass scales are important when we do the bulge to disk decomposition or to component, let's say, of elliptical galaxies. So the magenta line here shows the bulge component that is almost a power law in the size stellar mass relation, while the red is just the total relation between the size and the stellar mass. You can see that, up here mainly galaxies are just dominated by bulge, while down here you can see that this component starts being important. There is some effect. We see also a difference in the disk. So these are SCD galaxies, spiral galaxies, and these are the disk of spiral galaxies. Mainly above 2 × 10⁻11 we don't have a spiral, so we are dominated just by big bulges there. And the second also, the scale down here seems that there is a flattening in the size of the spiral galaxies. So this 2 mass scale seems to matter not only for elliptical galaxies but also for spirals. And a little bit more recently, Capellari et al. With the Atlas they found similar things. So here they have the kinematic profile of all galaxies, and you can see that there is a difference between the fast rotator and slow rotator. And they found two same mass scales, 310 to the 10 and 210 to the 11, where above 210 to the 11 solar masses we are dominated by slow rotator, where down here we have, these are bulges or elliptical galaxies, or S0, let's say, some of them, but they are fast rotators, okay? So there is a physics that goes on that change galaxy here. So what they conclude is that there is, you start from spiral, you know, then you start, here there is a growing in the bulges, but then to form the very massive galaxy here, probably you have the dry mergers. The question is, are they minor mergers or major? So to answer this, there has been some recent work using simulation by Itz et al., which they tried to compare what happened on the sulfur brightness profile of galaxies using the major merger 1 to 1, or 1 to 5, or 1 to 10. So this is definitely considered a minor merger. So you can see here, so you start from the black, that is you know, the initial galaxy, and then you go to the first generation when you are merging, and so on. Up here we go to generation 6. You see that for a major merger, after the first generation you already double the mass. The main thing to notice here is that for minor merger you don't change much the inner part here, you flatten the profile in the center, but you change a lot of the outer part, okay, because you mainly put galaxy star on the outer part of the galaxy. So the big change that you get in this profile is on the Sersic index. The size change a little bit, increase a little bit on the minor merger, but it is the Sersic index that change a lot. And that is what I will focus. So this is the same thing, just to show the evolution in the size. So if we start from 10 to the 11 solar masses, if we double it, okay, we have a change in size about a factor of 4. Velocity dispersion, depending if you have a major merger or minor. So in the case of minor merger, you keep the velocity the same, of you change it by a little bit, 10% or so. Major merger instead, you tend to increase velocity dispersion, but the big change that you have is in the Sersic index, okay? At least in this simulation. When you change by factor 2, you go from 11, 11.3, you go from a Sersic index of 4 to a Sersic index of 9. So now the point is, where do I start here? Do I start at 4, do I start at 3, or whatever? There are several work that they claim that high radius galaxies, they tend to have a little bit lower Sersic index. In this paper, they claim that also if you start at lower Sersic index, the variation is roughly the same. By factor of 2, you change the Sersic index by 5 at least. Okay, so that is what I wanted to test. So as I said, we already seen this scale, mass scale important for the size, for velocity dispersion, other parameters. We see the same also for the Sersic index. Okay, there is a change in the Sersic index. More massive galaxies, they tend to have larger Sersic index. Okay, so now I hope that you try to follow here. So this is Sersic index versus velocity dispersion, and here I divide in bin of fixed stellar mass. As you can see, these are mainly flat lines, and this instead tend to curve up. So galaxies that have larger Sersic index, they tend to have smaller velocity dispersion, a fixed stellar mass. Similar, you can see in this plot. Okay? So for the massive galaxy, we see that there is a difference on the Sersic index depending also on the velocity dispersion. So what I think is the following, that the galaxies that are assembled by minor mergers, they don't change their velocity dispersion. So velocity dispersion will be low, but they increase the size and they increase the Sersic index. We have to be careful because there is also variation on B over T. So these are dominated by bulges. Here we can start having like a rotational component, as we saw also from the work of Atlas, of Capellari et al., the Atlas people. And the same thing we see in the Cersei index. If we take just the budget component, it's more a power law. Instead, the total Cersei index gives us this curvature. So when there is this component, we have also an increase in the Cersei index. So what I think that happened is that this increase in the Cersei index at the brighter or large masses is due to minor merger, accretion of minor merger on the outer part, while this downturn that we have at the lower sigma, this is due mainly to presence of rotational component. Okay. And the other thing that we see here is that there is a dependence also on the specific star formation rate. Galaxies that have a little bit lower Cersei index, they tend to have a little bit lower specific star formation rate. Okay. So this goes in the same way that if you make up the outer part of your galaxy with a smaller system, they should be a little bit younger. So what about the high compact redshift galaxies? So now this we play with the toy model, but I will show you that if we put really the galaxy more or less it works. So based on the simulation that we have there, a galaxy that is 10 to the 11 should increase a lot the Cersei index, and they should increase a little bit the mass, so it could go on this region of the high Cersei index that we see at low redshift. Similar in the size, we can move up a galaxy up to this region, and this is a little bit more complicated, but these are the points from Belli et al. 2014. And we can see this is velocity dispersion, this is the size, and here we do a fixed stellar mass and fixed Cersei index. So it's a complicated plot, okay. But mainly these are the low Cersei index, and are the high Cersei index galaxy, given the size velocity dispersion. So then we have different stellar mass, but if we start from a galaxy that is 10 to the 11 with a Cersei index of 3, we can make it to go up to a 210 to the 11 with a Cersei index of 8. So now the question is, do we see enough galaxies? So there is this nice work of Van der Velde et al. 2014, where they look at the number density of galaxies that are compact, more compact and less compact. And so I just got these two numbers, redshift 2, that the red sample and the black sample there, and I plotted the line here. And this is just the cumulative number density of based on the Cersei index. And if we look for the sample that is stellar mass larger than 5 times to the 10, is this black dotted line, we can see that we cannot get the number above 6 or 7 that they measure at high redshift. So could be that these high redshift compact galaxies are actually this large Cersei index or low redshift. And let me jump this. I want just to say a word about the dependence on the halo mass. There is the Young catalog many people are using. So the problem of changing the photometry is that now you have kind of to modify also the catalog. Because the first thing that I tried to do was this one, so to get the Cersei index, stellar mass, and plot at fixed and halo to see if there was some variation. And you get this weird trend. That is because you get a little scatter in the... So what you have is a really tight correlation, one-to-one correlation between the total luminosity and the halo. So now if we change the total luminosity, you have a problem there. So what I did was to sort the new total luminosity with the halo. Although I would like to talk more with people just to see if that is okay. If I do that, I get this. And here you can see a little, it's small, but there is a little trend that galaxies that live in a larger halo, they tend to have a little bit smaller Cersei index. But I'm still not sure about if it's exactly the right thing to do to sort in this way. Okay. And about the satellite and central, I don't see any difference in the properties, except for the specific star formation rate, which is related to the age. I see a little difference, but that's it. And these are the conclusions.
So I have a couple questions. So I guess the first question is, I mean, the Sursich fits that you showed look like they make a heck of a lot of sense. To which extent does just a really super large aperture photometry agree with the Sursich results? That's the first question. And then the second is, you showed at a given set of mass that that if you had high dispersion, you had lower Sursich index, which makes it seem like there's a diversity of merger histories, such that the big guys can get big either by eating a comparable friend or lots of little guys. And now you've got lots of room in your mass function to allow major mergers to happen, because before you've got so many more massive galaxies that you can have a lot of majors and not violate any constraints. So to which extent does that kind of reckoning of size and Sursich index and mass function evolution all hang together? Is this kind of artificial thing of big guys can't have major mergers, has that more or less gone away?
No, I think that, honestly, what I think is that you have a little bit of everything. So you have some galaxies, so when you look also images of cluster at high redshift, often you see two big things close. Okay. So you see, there are several papers now that you can see that there are big. So major merger, I'm pretty sure that happened. And so what I think is that the really bright, the one with the very large velocity dispersion, those systems probably were made by, or they had in their history some major merger. Then they keep accreting, okay, but the major merger was, important for them. There are other galaxies that they have very high stellar mass, but the velocity dispersion, you are around 180 to 100. Okay, those galaxies, I don't think that the increase in mass and size is reasonable for this velocity dispersion that you have. So those, I think, that are the objects where minor merger were very important. Okay, so that is why I think there is a little bit of, and that is, I think the Sursich index is a good parameter to separate the cases. Okay. About your first question, so the problem of, so first of all, the big problem is to get, for bright, especially nearby galaxy, you need a large cut frame, okay? Otherwise you're affected by the sky. Then you go to the profile, okay? The question is, at this point, are you going to fit, where do you stop? What do you consider the light of the galaxy? Is the intercluster light part of the galaxy? Is part of the cluster, not part of the galaxy? These are all open questions. With the slow photometry, we cannot go deep enough to really detect the intercluster light. My opinion is that this large Sursich index that we see is not intercluster light, it's too bright. You start seeing really the surface brightness deviating from even a Sursich index of 4 or 5 at 23.5, okay, in surface brightness. So the sky is like 26, right? So it's still very bright. You are way above the intercluster light. Intercluster light start mattering at a dimmer surface brightness. So it's definitely important to get the right profile.
So there was a question over there in the front.
Oh, yeah, I had basically a related question. So if you were talking about this, I think you might have just answered it though, but my question was, if you were increasing the stellar mass based on changing the fit here, are you adding more stellar mass more to the outside or more to the inside, or uniformly?
Yeah, so the Sursich index, so definitely is on the outer side. Okay, but you can change also, because Sursich index increase if you change either the outside or you become steeper in the inner part. So it's a combination of the two. Compared to Sloan, what you get here is an increase in the outer part of the galaxy.
And that's a factor of 2 in the total mass.
Yeah, it can be large.
In front.
So the main question I have actually is whether we should also be worried about this with the higher redshift samples that people have used. Because people have for a long time, when you just use the Sloan as is, or as was, I should say, there was very little evolution at the massive end, and that had a lot of implications for discussions. And now, if the high redshifts don't change, but redshift 0 suddenly becomes your new version, that will change everything.
Yeah, so we did a simulation. We have a paper also, a bunch of simulation on this to test the code and to see also how it changed in different conditions. So we ran the simulation with HST condition, for the high redshift sample. So we see that it shouldn't be affected too much. Okay, I haven't really worked with the data, but they should be able to get properly the profile because they go deep enough. Because, as I said, this curvature that you have, this outer part that you have, is not very dim. We are not talking about intercluster light here. So I don't think that they are really missing stuff at the high reddish. I think that if they see small galaxies, it's because actually they are small.
So,
it's not that
so
they...
the upshot is the massive end of the mass function has evolved dramatically since Redshift
Yeah,
1.
I think really...
Which it bloody well needed to. So it's good that this has gone away.
Okay, so Jochen, we're going to go back over there.
So,
Jochen, then.
when you compare the mass functions, there's also the Baldry data, who also did Church's fits and agreed
Yeah.
with the Petrosian
Yeah, no.
data.
So the Baldry data, if you look at the luminosity function, okay, of the Baldry, the problem is that they don't go very deep, okay? So, but the part that they compute is really overlapped to mine, okay, on the surface, the luminosity function. The problem is when you go to the stellar mass function. There was another work where, they said, oh, we are close to the Baldry in the stellar mass function, but they use the C-model magnitude. C-model magnitude is fainter than the Cersei, so they couldn't have got the same stellar mass function. The problem is that you have the stellar population that goes inside the stellar mass function. Although you have the same IMF, okay, now depending on the stellar population, I have a paper that I show that the stellar mass function, the uncertainty in the stellar mass function is at least between 30 to 50%, okay. They can tell me what they want. If you take all different people that compute the stellar mass function with different libraries, okay, the agreement is on the order of the 30%, just because of the templates that they use. Okay, there is a huge uncertainty in because what you compute is M over L, right?
But then it has to be very mass dependent, because at low mass end you agree with the Petrosian,
Yeah,
and Baldry agrees both at the high and low mass end with the Petrosian.
Yeah, so there is the two things, okay. So the variation that I see here is huge, right? It can be a factor of almost 2. The 30% is much smaller. So I would say that there is a 30%, you see that even at low masses, okay. The 30% is just due to the stellar population. Okay. Then you get a large uncertainty due to the luminosity, because the stellar population compute M over L. Then you have to multiply M over L by L. So the large uncertainty is in L, 30% M over L, roughly. Okay. And then you have the problem of the IMF. That if the IMF depend...
But they all assume the same IMF, I just don't understand.
Yeah, exactly.
I don't really understand your answer, but we'll talk later.
Yeah, a question over there.
I have a very short question. I have a reading comprehension question. In your last point, you're saying that if the evolution at large masses is dominated by minor dry mergers, then we would expect these relationships that you list in the second bullet point.
No,
Is that correct?
No, so what I'm saying that maybe, so my main conclusion here is maybe the galaxy that the massive galaxy with large Cersei index that we see, maybe they are the one that derive from the compact high redshift galaxy. Because I'm not sure, I'm just saying based on the simulation, it seems that for this galaxy to become larger, they must have accreted by minor mergers to become so large. If that happened, the Cersei index must have increased a lot. So if we see them at low redshift, if they are not still compact at low redshift, maybe these are the larger Cersei index that we see. I'm just putting there, I'm not sure about that.
Okay, last question.
So I have a very naive question. If you correctly say that Cersei indexes, especially at high end, so dependent on both the inner and outer part, why not use more parametric compactness parameter instead of trying to fit single Cersei's?
Yeah, so what I prefer to use is not the single Cersei, but is the Cersei exponential. Okay, that is even more parametric.
Why not an R90 over?
Where's the edge of the galaxy?
Yeah, so that is the problem. So when you have these big galaxies, the problem is to get the outside. Where do you stop? Okay, you can miss, but that is the problem of Petrosian magnitudes. Okay, you can miss part of
But
of
is
the
it,
line.
for example, your results consistent if you would not fit the inner part? Because if you have a large n value 10, then I mean, it will be highly dependent where you have a lot of signal in the inner part.
Yeah, so
did you try to just not fit the inner part and then?
yeah, that I haven't tried, but I tell you that just I look at many of this profile, okay, I would say that the result wouldn't change much, because what we see here is really that compared to the debaculaire, okay, is really the outer part that push up. It's not the inner part.
Okay, so we're going to break.
I can show you the profile.
Okay, we're going to break for coffee. We'll be back here at 11:45. I think people need a slightly longer coffee break after last night. I want to thank you again for a very interesting